Hey guys, this is Noah Housley again with 302 Help, and this is section 3.3 from the lecture, just to get some concepts down and why things work how they do. So first thing, this whole section was talking about inverse matrices, and so really the point of inverse matrices is it makes it easier so we can solve linear systems. So how they work is first we need to know that A times B is equal to B times A. This was from a previous lecture. That's just the identity of matrices, that it's not commutative. It equals an identity matrix where identity matrix is just, for example, it's ones on the diagonal and zeros everywhere else. It's called the identity matrix, I think, because when you multiply this by a matrix, you just get the same thing. It's like multiplying by 1. So that concept would come in handy. So when is a matrix able to be inversed? And well, you get it from this equation. So we have so an example, A, B, C, D. If you inverse it, what that looks like, what that's going to equal, is you switch the D and the A, and then you change the sign on the C and the B. Then you divide by AD minus BC. So if this is 0, then that's not able to be inverted. And so that would be when you can't, but when you can, then this division would be that. This is only for 2x2 matrices, so this is just a nice equation for that. So the question is, what if we don't have a matrix like that? Also, what is an inverted matrix? So the definition is that if we have matrix A times by the inverse of matrix A, it's going to equal the identity matrix. For example, and an easier way of thinking about this, since the identity matrix multiplied by any other matrix is just itself, I'm going to call that 1, since 1 times anything is like itself. And then if we had 1/2, and the inverse of 1/2 is 2, so I have 2 over 1 there, if we multiply it, it's going to equal 1. And so it's almost like doing math theory. You do, or not math, of course it's math, but I mean like just normal algebra. Say we had a matrix here, and then we multiply by the inverse, and we get 1. So I'm going to explain more on that in just a sec. He briefly brought into elementary matrices just to say that we can do row operations on the identity matrix and the A matrix to get the inverse. So that just means that by doing elementary row operations on a matrix, it also affects the matrix that it equals in the product. So, for example, matrix A times matrix B is going to equal the identity with any other row operations that you did to it. And if you did row operations over here, I put a little E1 for row operation, elementary operation. More like identity, this would be a better way to put it. So identity matrix with row operations times B is going to equal B with the same row operations. And so that's what he just did. So that way he could show, we can do row operations on a matrix and to its identity matrix, and we'll get the inverse. And I'll show how that works in just a second. Right here. So one elementary row operation on the identity matrix. Okay, so here we got, actually that doesn't apply to this. So let's start with this equation. These are elementary row operations, so 1, 2, and then so on and so forth till k. And A equals I. So what I'm going to do is I'm going to make this equal matrix B. So technically I have, where is it up here? Matrix B times matrix A is equal to I. So if I treated this like I did this equation, what if I wanted matrix A? Well, all I have to do is I have to just multiply each side by the inverse of B, just like if I was solving for this. If I wanted that, then I just had to multiply each side by its inverse. So that's what I do. And I multiply B times B inverse, and then I times B inverse. And since I multiplied by any matrix is just that matrix, this just becomes B inverse. And then B times B inverse, since the definition of here is A times A inverse equals 1, and that's for any matrix, then B times B inverse is going to just equal I. So here we have that I equals A. And since I, again, just like 1, we get that A equals B inverse. So that's just a funny way of saying, so all these elementary row operations, which can be inverted in and of themselves. So for example, if you multiply a row by 2, then you can divide that same row by 2. It can be inverted. It acts like a matrix. And so you can invert, and then it'll equal I, and then you'll get that A equals B inverse. Okay. All right. So hopefully that made sense. It made sense in my mind. So if you can't get to the reduced row echelon form when you're doing all of these row operations on this super augmented matrix, then there is no inverse. And you can check if you got the right inverse by multiplying it by the original matrix that you had by what you got, and you should get the identity matrix. Okay, so hopefully that helped. This comes in handy when it's like huge matrices, I guess. Okay, thanks for watching. Comment any questions or anything I can do better.